everyone, my name is Marouan Bouali. I'm a research scientist at ORBTY, a startup based in the state of São Paulo, Brazil. And in this presentation, I'm going to talk about a new approach for level 3 SST datasets from satellites and optic observations. This approach is quite general and it can be applied to many other metocean parameters like wind speed and direction, atmospheric water vapor, as well as ocean color. So the context of this presentation is the increasing interest in ocean dynamics, which usually focuses more on SST gradients than SST itself, and therefore requires SST fields with a consistent spatial distribution. Level 4 SST datasets have been extensively used for the analysis of SST gradients, but one major limitation is that the complete coverage comes at the expense of overly smooth SST features. On the other hand, level 3 SST products only use satellite observations, so they are expected to not affect the representation of SST features captured at level 2. The most common approach used to generate level 3 datasets, at least from a user perspective, is time averaging, which is also known as compositing. While this is a statistically coherent approach, it does introduce artifacts that are going to affect the spatial distribution as well as the temporal variability of SST gradients. So here's an example of a 3-day composite map of wind speed derived from ORBTY. We can easily notice the edges of the sensor swath and significant patchiness in the data. The reason why I'm showing wind speed here is that temporal variability is higher than that of SST, so these compositing artifacts tend to be quite pronounced. They can also be seen in SST, but only when we are restricting the range of SST values to be displayed. At ORBTY, we've been working on a way to generate level 3 maps without introducing these artifacts. And the result of this research is the M3DFS, which stands for Multidimensional Dynamic Data Fusion System. It's basically a 3-dimensional variational model highly inspired from computer vision methods. It's composed of 2 fidelity terms. The first one is a geometrical constraint on the solution U, and the second term is a statistical constraint, with both terms being balanced with a fixed coefficient mu. So what the M3DFS does is that it allows us to go from something that looks like this to something that looks like this without interfering with the statistical characteristics of the data at both global and regional scales. Now, going back to SST, this is the experimental setup for the results that I'm going to show you. We used synoptic level 3 SST derived from ORBTY, provided by remote sensing systems, and we generated level 3C datasets at different temporal resolutions using 2 methods, the standard compositing approach and the M3DFS. And then we computed the magnitude of SST gradients estimated with central differences, and we analyzed the spatial distribution and temporal variability at the global scale. This is the spatial distribution of gradient magnitudes computed on a 3 days composite SST for the period from the 1st to the 3rd of June of 2022, and this is the map obtained using the M3DFS. As I switch back and forth between these 2 maps, we can notice a slight cleanup in the SST gradients without any perceivable change in the main ocean fronts. And in fact, if we take a look at the map of the absolute differences, there doesn't seem to be any spatial correlation between absolute errors and SST gradients. Now, as we decrease the temporal resolution of the level 3 SST over which we're computing the gradients, we would assume that the impact of compositing artifacts is going to decrease as well. But this is actually not the case. So these are the gradients computed on a monthly SST for June of 2022, and this is the same map obtained with the M3DFS. And now the difference appears to be a little bit more obvious compared to the 3 days temporal resolution. And again, we can check this by looking at the map of absolute errors. One thing to be noticed here is that the errors start to accumulate over specific areas, which likely correspond to regions with high temporal variability or large uncertainties in the SST retrieval. So definitely something to investigate in the future. So to evaluate the quantitative impact of compositing artifacts, we analyzed the temporal variability of SST gradients for the entire year of 2022 for all 3 temporal resolutions and the 2 methods. Here's the time series of SST gradient magnitudes averaged over the entire globe on the left panel, and on the right panel we have the absolute error in percentage introduced by artifacts for the 3 days temporal resolution. We can see that, as expected, by getting rid of compositing artifacts, the M3DFS brings down the overall magnitude of gradients. And if we take a look at the right panel, we see that for 2022, this corresponds to a systematic error of the order of 10%. And just as we've noticed in the spatial domain, the error from compositing artifacts appears to increase as we increase the temporal window of the level 3 SST. The time series for the 3 days and monthly time window show that the median error in SST gradient magnitudes over the globe for 2022 increases from 10% to almost 15%. So this is the conclusion of this short presentation, which you can find in the corresponding poster. What I would like to mention here is that this is a highly compressed summary of an upcoming GRIS talk scheduled for November the 30th of this year. And in that presentation, we'll show the impact of compositing artifacts on SST gradients as we go from level 3C to level 3S, from global to regional analysis, and from microwave to high resolution infrared data derived from sensors like MODIS and VIRS. So thanks for watching, and if you have any questions, feel free to contact me.